So just for the first 15, 20 minutes today, yesterday I introduced what the assumptions or what the motivation behind Landau Fermi liquid theory was. So for the first 20 minutes, I'd like to kind of explore the consequences. If you take, so just to recap, what we said yesterday was that there are occupation numbers called, denoted by NK alpha. And these were occupation numbers that parameterize the interacting eigenstates. We introduced the notion of a quasi-particle, a quasi-hole, and then towards the end of the class, I tried to argue to you that at least at really low energies near the Fermi surface, these are well-defined excitations. We calculated a lifetime to first-order perturbation theory, which we call tau. And we said that it scaled as the -2 power of the amount of energy in the excitation, delta E. Right? So just a comment, if you went to higher orders in perturbation theory, tried to consider higher order processes and scattering, this is only going to get better and better. Okay, so it's going to diverge faster and faster as delta E goes to 0. This was what gave us hope that perhaps this idea of quasi-particles and this assumption of a way to treat the interacting problem might not be completely, it may be useful. Okay, so let's run with it now and ask, how is this useful? How do we use this when we do experiments to explain what we find when we measure interacting systems? So this assumption tells us that the energy of a state with these occupation numbers can be expanded about the ground state as follows. Star. K prime beta. Okay. Energy of a state with these occupation numbers is the energy of the ground state. Remember, the ground state had occupation numbers 1 if K was less than Kf, 0 otherwise. Plus, and these delta n's are the difference in the occupation numbers with respect to the ground state. Okay, so we're expanding what a low energy eigenstate, low energy as compared to the ground state, what its energy looks like in terms of delta n. So this is the term linear in the number of excitations above the ground state, and this term is quadratic. Okay, so this energy here is the energy of a quasi-particle. And this F here represents interaction between quasi-particles. QP is a quasi-particle. Okay? Yeah?
Please, I'm not entirely sure how the lifetime being proportional to the inverse squared of the difference in energy gives our assumption legitimacy in some way. I wasn't sure about that.
What it's telling us is that we can meaningfully talk about quasi-particles until some time scale set by delta E to the -2. Right? So
Okay.
I can the notion of an occupation number of a quasi-particle is well defined. It's not well defined at arbitrarily long times, but it's well defined to a time that's diverging as you head towards the Fermi surface.
Okay.
That's what this is telling us. So you should take this formula as being valid until this time scale. Once you look at times longer than this time scale, the quasi-particle can just decay, and it just will vanish. There will be no conserved occupation number.
Okay.
That's
All right.
right. And so for the rest of the class, we're going to ignore the fact that quasi-particles are not truly well-defined at really, really long times. And we're only going to think about the fact that this is good enough. This means we can talk about effectively, basically conserved quasi-particles at really, really low energies. And so that will be the rest of the class. OK. And so just to remind you, in lecture 1, when we did Hartree-Fock, we found there's a very similar form for the energy that we derived for the variational state that was also parameterized by NK alpha. OK. So I'm just going to point out two properties that we can derive from this relationship. One, effective mass, two, specific heat. And then I'll just indicate in general where Landau Fermi liquid theory can take you. And the next part of the class, by the way, is on the quantum Hall effect, which is why I'm rushing through this. All right. So I now know what the energy cost for every eigenstate is. So in particular, at really low energies, when there are no other quasi-particles in the system, psi k alpha star, as we said, was the energy of a single quasi-particle. And I can expand it near the Fermi surface. So I can say this looks like the Fermi energy plus OK? So this is just expanding. This is some function of k and alpha spin. And I'm just expanding it near the Fermi surface. So this is what's called the Fermi velocity. Equals Vf. And we can always write it in this suggestive form. Kf over m star, we write it in the suggestive form because we're following whatever we did for the non-interacting problem. Right? In the non-interacting problem, Vf was just Kf over m was the mass of the non-interacting electrons. So we write it in the suggestive way, so that psi k alpha star then looks like this. OK? Yeah?
Is there any reason why I might expect that the first derivative is non-vanishing at the Fermi momentum for a general setup?
So I guess the assumption is that this is a smooth, well, good, just a good function at the Fermi momentum. So maybe to give you an example, I didn't stress this, but I encourage you to go back to our Hartree-Fock calculation and calculate this. Yeah. You'll actually find that it diverges in the Coulomb case so what diverges? Vf is divergent at k is equal kf. So it need not be that this is well defined, but in that case it's a sick theory. In theories that we're interested in, this is going to be well defined. I'll give you by connecting it to the specific heat, I'll give you a very experimental way to measure this. So if you can measure it in an experiment, it's well defined. You can do this. Okay. All right. So I guess for the moment, assume that it's non-zero. So then this is the leading term. And then you see that the energy of a quasi-particle looks just like the energy of a particle in the non-interacting problem, as long as m star is replaced with m. Right? So everyone sees that. So we've written it in the same way as if it was a non-interacting problem. Only difference, there's a new mass called the effective mass. So this means when we do a specific heat calculation, let me just, in the same spirit as what you did in tutorial 1. So for the non-interacting problem in tutorial 1, you calculated CV, right? Anyone? It was proportional to T, OK. Do you remember how it depended on the mass of the electron? What's that? it was just M. Okay. I mean, I guess you could guess it from dimensional analysis, but so this and then there's factors of kf's in here, which we don't care about. So when we actually, let me just write the actual formula. KB squared kft. Indeed, the important dependence was on temperature T that we stressed. That was linear in temperature. It also happens to depend on M as linearly in M. So this was the result for the non-interacting gas. And now, so let me write that, non-interacting. And now we're going to work out from this phenomenological theory here. So we just have like, an expansion for what we think the energies are of the excitations in terms of parameters psi k alpha star and this f. Okay, so I want to emphasize that these are parameters. I say we're doing a phenomenological theory because we're going to fit what these parameters are, and that's going to be our theory. And so the specific heat, I'll just show you right now, is going to measure m star. So that's the way you do a measurement of specific heat. Okay, you know one parameter in your theory. Then the spin susceptibility, which I'm not going to calculate, is going to measure a parameter about f. So then you put that in. Compressibility, measure another one. You put that in. Okay, so let me just show you at least the specific heat. So specific heat was defined as CV is 1 over E delta E delta T at fixed volume. K alpha. At fixed volume, right? So E here is the E on the board there. Okay, and so let's just look at the two terms. This term is just taking a derivative of that formula up there. And okay, so this quantity has the interpretation as the energy of a quasi-particle in the presence of other quasi-particles. Okay, so this term corrects the bare energy that you would have said because the quasi-particles interact with one another. Okay, so now at really low temperatures, we expect that because these quasi-particles, we argued yesterday, themselves satisfy a Pauli exclusion principle and are fermions, we expect this to be true. Maybe I'll just write, okay. That is, we expect the average, and I put a double brace here because I'm trying to, it's a thermal average. Okay, I'm not taking the expectation value in any state or anything. This is the thermal average. The thermal average of the occupation numbers of quasi-particles follows a Fermi-Dirac distribution where the energy is this energy. This is the energy of a quasi-particle. Okay? And so, again, like we did in Hartree-Fock, we have something like a self-consistency problem. The energy of a quasi-particle itself depends on the numbers of all the other quasi-particles, the average distribution of which itself depends on the energy. And so, as before, we would have to solve this self-consistently to get the energy and the occupation number. Okay? But at really low temperatures, we're actually saved, and we're saved for the same reason that the Sommerfeld expansion works. At really, really low temperatures, notice that this delta N here is the difference in the occupation in the ground state versus in thermal state, and so it's something like a derivative. And you did this on Monday. You used the fact that if this was a Fermi-Dirac distribution, the derivative is really peaked I don't know if I got the right sign, right? But there was this, you noted that the difference between the 0 temperature one versus the finite temperature one had this peaked form right near the Fermi energy. And this was important in evaluating functions which had the derivative of the Fermi-Dirac distribution. So in exactly the same way here, you could use that exact algebra that you did and to show that this term at really low temperatures is proportional to t squared, okay? Using the Sommerfeld expansion. So that tells me that at really, really low temperatures, I can ignore the fact that the quasi-particle energy is modified by the presence of all the other quasi-particles, and I have that this relation is true. Okay, so once this is true, that's great, because I know this looks just like the kf times kf over m star. It looks just like the non-interacting problem that I solved for on Monday, except m is replaced by m star. So without any more algebra, all I do is I write down the result derived for non-interacting electrons and replace m by m star. Okay, so to backtrack again, what we did was we used the energy function for the quasi-particles in the interacting gas to derive a thermodynamic quantity, which is a specific heat. And at really, really low temperatures, we found that it has the same form as a non-interacting problem, with the only difference being that there's a new parameter that's appeared here called the effective mass. Okay? And so this is an experimental measurement of m star, and if you wish, the Fermi velocity through that formula. And so in helium-3, this is about somewhere between 3 and 5, m being the mass of a free electron, m naught. Okay, and so this is measurable, and the fact that it's so different from 1, which would be the case for the free gas, is telling you that interactions are important, right? So somehow it was not that we're perturbatively changing the interactions, we've almost forgotten them, it's almost free. No, it's that there is a free description despite interactions, and how big this number is telling you that. Okay?
So in some sense, you can always do this. That you can always, effectively, you're hiding a lot of information inside m star.
Yeah.
So you can always have this description in every theory. Not.
No, so let me say a few things.
Especially Landau for me.
Well, okay. So from that theory, you will always get, for example, this t dependence. So if, for example, you'd experimentally measured, no, CV actually goes as t squared, then this theory doesn't work, right?
Okay.
So it's gotten, there's more information than just, oh, we can put in whatever parameter we get there. It got the right temperature dependence, and that's because it correctly mapped this somehow to the non-interacting problem. Now, indeed, you're right that there's a lot of information hidden in these effective parameters. And so that's my next point, which is the predictive power of this theory is going to be there only if there are only a few parameters that you need to measure. Once you measured a few, and if you basically know what that expression is, then you can use it to predict new phenomena, and then check. That's now a check on the theory. So at the moment, it's not a check on the theory in the sense that, okay, it predicted the right temperature dependence, but we've fit a parameter. Similarly, I'm not going to go through it in the interest of time, but similarly, other thermodynamic measurements like susceptibility and compressibility fix parameters in F. Okay? For helium-3, it turns out that there are only a few parameters in F that need to be fixed for a good description. So if you took my word on that, I want to talk about so first, what does the Landau theory predict then? So what it predicts is actually not an equilibrium property, but a non-equilibrium property. And it's known as zero sound. So okay, this is like the ideal gas that I'm sure you've done this calculation for. The Fermi liquid supports longitudinal compressions of density. That's sound. Right? So there's a speed of sound predicted in this theory. And Landau's theory, which says that the quasi-particles interact with one another, actually corrects this speed at higher frequencies. Okay, and that correction can be, once you do a few measurements of this and a few more parameters, that correction is completely fixed, and now that's something you can measure and check. Okay, so we're not going to do that. It actually involves going through a Boltzmann treatment that I'm not going to do today, but I just want to tell you that that's the first non-trivial test of Landau's theory. And in helium-3, it works surprisingly well. Okay, so that's one. Two is, remember this quantity we mentioned yesterday, Z? It was called, Z was the, we said it was the overlap between the CK, between the state created by the bare electronic operator above the ground state, interacting ground state, and the actual eigenstate. There was this overlap that we wrote down yesterday. We called this quantity Z, and we said that it was non-zero. Actually, I don't know. Maybe that's what we call Z. Yeah. And then we said that it was bigger than 0 and less than 1, and that this is a non-trivial fact of Fermi liquid theory. So this quantity is also measurable in the lab. Again, that's maybe another a test for the quasi-particle theory. And the way this quantity is measurable is through tunneling experiments. So when you try to tunnel an electron into a system, basically what you see is the spectral function of the system is what you directly see. So let me try to just, I'm going to say this qualitatively because I'm not going to do the algebra, but hopefully it'll make some sense. So you've all done a bunch of field theory that's told you that if I took Green's functions, which are, C, K, time ordered. This is a Green's function you've all seen before, right? This is the time ordered.
Excuse me.
Yeah.
So what was the difference between A and C operators? So you.
Oh, Q, sorry. So Q is the actual, C is the bare electronic operator in the non-interacting case, and Q is the actual genuine quasi-particle creation.
Oh, okay.
Yeah. Okay. Okay. So this particular Green's function, which is a Green's function that is related to, at time t is equal to 0, destroy a fermion or create a fermion, and after some time, so if you destroy a fermion at time t is equal to 0, after some time tau, you create it again, right? And so this is a Green's function which measures the, it's called the spectral Green function, measures, what it's doing is it's asking what are the frequencies at which the system responds, okay? So if there is whenever you see a resonance in the Fourier transform of this object, what that means is if you see a resonance versus frequency, that means that there's a way for you to put a lot of energy into the system at this frequency. Okay, so maybe the stupidest picture is to go back to think of a spring and a driving force for the spring, right? So we all know in a spring, K is a spring constant, M is a mass. There is a special frequency associated with the spring, which is the natural frequency of the spring. So when you try to drive the spring at different frequencies omega star, so you're imagining there's a force that you apply, which is cosine omega star t, you'll find that most of the time you're unable to inject energy into the system, except when omega star exactly equals to omega. Right? Everyone's seen this before, and then there's a sharp resonance because this is the natural frequency of the system, and you're able to inject a lot of energy into the system. Okay, so a similar plot for, now think of an electronic system, and what you're asking is the same thing. At what frequencies am I able to inject a lot of electrons into the system? Okay? And if you see a peak in it, that's telling you that there's basically a particle at that energy associated at frequency. Is this not making much sense? Okay, I'll just say this and move on. It didn't make much sense. That's okay, because I didn't actually do it in detail. What I want to tell you is that if you see, when you do experiments on these systems, you actually find that there is a peak of well, actually it's spread out a little bit, and it's a peak of area Z, and it's actually interpreted as a presence of a quasi-particle, because if a quasi-particle is a sharp resonance in this spectral function, and when you do experiments, you do see it, and you can measure this Z. So this is one way in which you further test this idea of a quasi-particle, the idea that the system shows sharp resonances at certain frequencies, which has an interpretation as having particles at that energy. Okay, that's what I want to get across.
So do these peaks get sharper with stronger interactions or weaker interactions?
Well,
how does the strength of the
actually the width of the peak is set by this lifetime that we discussed, right? Okay. So if this particle was an infinitely long-lived particle, there would be no spread.
Yeah.
It would be a sharp peak. Okay. That's not true. It's not infinitely long-lived, as we saw. So there's some spread associated with the fact that, and think of this like the oscillator with a little bit of dissipation, right? If you've seen these functions before, with the oscillator, a little bit of dissipation, it spreads out the resonance by a little bit in frequency space. Similarly, because the quasi-particle is not infinitely long-lived, this thing is spread out a little bit. But the measure of interactions is in how big Z is. If Z is very close to 1, it's almost like the non-interacting problem, because right, Z1 was exactly non-interacting. If it's very far away from 1, it's typically, I think, somewhere between somewhere like 6 to 8. Then it's telling you that interactions have actually modified this. And there'll actually be some background part of the spectral function, which is a continuum. I didn't talk about it, but I just want to emphasize that you can measure these spectra, and resonance of these spectra tell you there are quasi-particles in the system. So that's kind of further evidence for this picture of quasi-particles. Yeah.
Is this also a way to determine the effective mass?
Yeah, because this quantity here near the Fermi energy, yeah. That's right. Okay. Any final questions or any burning questions on Fermi liquid theory? Because otherwise, I'm going to start a completely new topic. No? Okay. So, quantum Hall. Okay, so far we've been talking about metals, right? We start, and one definition of metals, which is through their transport. We were talking about systems with such that the resistivity tends to a constant as t goes to 0. Okay, so what is resistivity? Resistivity is just, as you all know, R is resistance, rho L over A, whose length is, everyone has seen this before, right? Ohm's law kind of thing. So a metal is one which satisfies Ohm's law, and it just has finite resistance and resistivity even at really low temperatures. Okay? Now we're going to switch and actually talk about not metals, but insulators. So they don't support currents at very low temperatures. They have very large resistances at low temperatures. And we want to explain this basic experimental observation for a special kind of insulating behavior. Okay? Sigma here is conductivity. How is it defined? It's defined as, so if you have current density, Jx, Jy, the conductivity relates current to electric fields. Okay? And roughly speaking, it's the inverse of the resistivity, okay? And it's related to the resistance. So I will come back to these definitions in a little bit more detail, but let's get the phenomena first. What's happening? This is the definition. So there exist real transistor-like devices in which there is a 2D electron gas. So there's a 2D electron gas subjected to strong magnetic fields B, which are perpendicular to the xy plane, in which it's seen that the sigma xx conductivity, okay, goes to 0. So this is kind of like insulating behavior, whereas this transverse conductivity is quantized. And this is the surprising part. This transverse conductivity is quantized. Nu is quantized to like 1 part in 10 to the 10. It's quantized to be either an integer or it's quantized to be a rational number. Okay, so this will come to the data that I've distributed in just one moment, and this will make a little bit more sense. But and I want to emphasize that this behavior is independent of sample, independent of material, independent of the amount of disorder, the particular value of the magnetic field. And this is known as the quantum Hall effect. Okay, so in a little bit more detail, first, it might help to understand the system a little bit more. So exactly what's being done. First is there is an electron gas that we'll talk about in just a moment, how they make it in the xy plane. Okay? So there are electrons in this plane. In the z direction, there's a magnetic field that's applied to these electrons. Then the measurement that's done is that there is an, so this is the x direction. Okay. In the x direction, one applies a voltage, and one then measures the current along the x direction and the y direction. Okay? Yeah?
When you say a 2-electron gas, it's, it's embedded in a 3-dimensional space.
I'll tell you, I'll just tell you in a moment how they make it. Yeah, it is embedded in a 3-dimensional system.
My concern is that even in the literature, they say it's a 2D electron gas, but when you treat them with interaction, you're using the full of interaction of the 3-dimensional space, right? Not the 2-dimensional space.
Yeah, but yes, I'll tell you in just one moment. Okay, so this is the kind of cartoon setup of what's happening. There's a 2D electron gas in a strong magnetic field, which is perpendicular. One applies a voltage in a direction and measures the current in the same direction, perpendicular direction. And then, V resistance is like V divided by I. Rxx would be Vx by Ix. Rxy is Vx divided by Rxy is Vy divided by Ix, I guess. Yeah. Or maybe the other way around. But anyway, so this is how one defines these resistances, which are related to these conductivities. And then one plots them. And so now just if you could see the sheet up that I distributed, this is the data that you get, okay? So a couple of features about it. The first thing that you notice is, so in the data that, this is, I think, from 1990, and is a part of, these were the people who discovered the rational version of this effect. It's their data. So a few things about the data that I'll just kind of show here, but it should be much clearer. So they plot Rxy in units, I think, of h squared over e. So it's dimensionless versus magnetic field in Tesla. And so two features about it. First is you see these giant plateaus, right? There are many, many of them, and they're all labeled by integers or rational numbers, nu. So that's the nu that we said here. Second, every time there's a plateau in Rxy, there is a dip in Rxx. Does everyone see this? These are the two features which are called the quantum Hall effect. One, plateaus in Rxy. This is the transverse conductivity or the resistance versus magnetic field. Two, every time there's a plateau, Rxx vanishes. It's non-zero only between plateaus. Okay? And this happens at just so many, many values of nu, both integers, 1, 2, etc., and fractions like 1/3, 1/5, 2/5, etc. Okay? And so this is what we're going to try to understand in the next, I don't know, 2.5 lectures. It turns out, first I want to explain to you why is this data weird, right? As such, presented like this, it's like, okay, I don't know, maybe this is just what electron gases do. So I want to first explain to you why is this data weird. We'll start with the classical electron gas and the classical Hall effect, and we'll see that we don't get a plot like this. Then we'll try to explain the integer quantization called the integer quantum Hall effect, in which we'll try to at least understand what the plateaus are in which nu is 1, 2, etc. And finally, on Friday, we'll see that to understand the fractional plateaus, we need even more exotic physics. We'll have to put in interactions, and this will lead us to topological order and anyons and things like that. Okay, so this seemingly boring data of some transport coefficients in the last 30 years has been like, it's been a big part of condensed matter because this is the only known example to date of a topologically ordered system in the lab. And so I want to build up to tell you why this is so and why this is so interesting. Okay, so first, let me just tell you how they make this 2D electron gas. That might clarify some questions about should we worry about the dimensionality, etc. So the physical system is actually a semiconductor system. It's a semiconductor heterostructure. And so heterostructure just means multiple kinds of semiconductors in layers. So if I plotted the bands of the system, just the conduction and the valence band versus the layer, there's 3 layers. This is like aluminum, gallium arsenide. So gallium arsenide is sandwiched between 2 layers of aluminum gallium arsenide. The conduction band looks like this. Valence band looks something like this. This is just cartoon. Conduction. We dope this aluminum gallium arsenide with silicon donors, which give extra electrons, and they all go and sit in here. Okay? So bottom line of this picture is through this layered structure, one is able to, in a very thin layer of gallium arsenide, there's still the YZ plane, right, coming this way. One is able to trap electrons in here. It's also known, this is known as a quantum well. And this is the 2D electron gas in the layer of gallium arsenide. Okay, so some numbers. Why do we call it 2D? Well, there are excitations allowed in the, so you notice that this is kind of like particle in a well, right? So I can solve the quantum mechanical problem in this direction, and I find that the spacings between adjacent levels, so E excited minus E ground state in the x direction is roughly at 1,000 Kelvin, okay? Versus the experiments that are done at cryogenic temperatures of like, so if you look in that data, I think it's like, I don't know, 80 millikelvin, something like that. So these samples are in cryostats, they're very, very cold, and for you to consider excitations in this frozen out direction, in this x, what I've called x, the temperature should be like order 1,000 Kelvin. So you don't worry about it, and you instead say that as far as this x direction is concerned, all the particles are in the lowest state, whereas they're free to move in the YZ plane, and this effectively gives me a 2D gas. Okay, so coming to your question about interactions and stuff, this does have a finite width, and so it is in 3D. We're not, and so one puts in the 1 over R interactions. Okay, so another remarkable thing about this setup is that the inter-electron spacing at the densities that they make, that they can have in this gallium arsenide layer, that's like around 8 nanometers. But the mean free path, which is the path that an electron travels between scatterings with impurities, right? So the mean free path roughly tells you how clean this 2D gas is. How often does it scatter off some impurities that we've not talked about? But this mean free path is on the order of millimeters. Okay, so just look at the like, I don't know, 7, 8 orders of magnitude between these two. An electron sees another electron every 8 nanometers. However, it sees an impurity from which it scatters off only every millimeter. Okay, so that means that the sample is clean enough, and the physics here is really going to be dominated by what the electrons are doing with respect to one another, and we can really not worry about, you know, disorder, phonons, all these other things that we think about in normal materials. So the phenomena that we hope to see here is, we hope, really captured by just 2D electron gas in a strong magnetic field. Okay? So that's the physical system. And a more modern realization of this effect has been in graphene. Graphene, as some of you may know, is actually a 2-dimensional hexagonal structure of carbon atoms. So hexagon. And it's basically benzene, but and so it's actually 2-dimensional, the electron gas, and you don't have to do any of these fancy things. And in it as well, the quantum Hall effect has been seen. Okay. All right. So that's the physical system, and now let's ask ourselves, you know, why is this transport data special? So to answer that, let's first see what the expectation would be for classical electrons in a magnetic field. Okay, so I have an electron gas in the xy plane, magnetic field in the z direction. And so electrons in a magnetic field feel a force called Lorentz force, right? Okay, so we all know what it does. We can write down these Newton equations. X dot, right? Double dot. Which is just saying that it feels a Lorentz force. And unsurprisingly, we find the result that the electrons will move in circular orbits. Is this better to see? Okay. So this is circular motion with the frequency known as the cyclotron frequency defined by EB over MC. Okay, so this is nothing surprising. The Lorentz force forces electrons to go around in circles. So no matter what the initial velocity is, the electron will follow a circular orbit. One thing we learn is that the period taken to complete an orbit is independent of the radius. That's what omega c is. So no matter how big the circle is, it comes back to the starting point after the same amount of time, 2 pi over omega c. And so that just means the electrons in circles of bigger radius will be moving faster with greater velocity. Okay, so that's the classical orbit of an electron. And so now what happens when we do the Hall experiment on these classical electrons? This, by the way, was actually done by Hall in 1850s, which is why the word Hall appears everywhere. So it's a simple enough experiment. You take this electron gas, and you, as we said before, you apply an electric field in one direction, which is the x direction. You still have a magnetic field in the z direction. Okay, and we've all solved this problem in undergrad. There is E cross B drift, right? So there is the Lorentz force wants electrons to go in circles. The electric field, however, is another force acting on the electrons. And so these forces balance, and the electron will drift in the y direction, right? So one easy way to figure out what the drift velocity is to just assume the answer. So assume the electrons are drifting in the y direction. So let the velocity v be v y hat. Then we know that for the forces to cancel, the force due to the electric field should be the same as the force due to due to the Lorentz force, right? So when I do this, I find the drift velocity to be E over B. By the way, if it's not been apparent, I'm using CGS units, which is why you see the speed of lights C's around. But I'll consistently use this, and it should be OK. So anyway, important point, the drift velocity is the ratio of E over B, independent of charge. And so now if you calculate the current, remember, is density of electrons n, charge of electrons q, times the drift velocity. Right? This is the formula for the current density in the y direction. The charge of the electron for me is minus e. I plug in what I have here for v, and I find that j vector is y hat, so that the conductivity, jy over Ex, which is sigma Yx, is minus NEC over B. Okay? Consequently, the resistivity, ends up being B over NEC. It's the inverse of that. And the signs will make sense. Yeah, we'll come back to the signs in a bit. But basically, if you thought about the matrix that I introduced here before, the sigma matrix, then the resistivity matrix rho is defined as the sigma matrix inverse. And so once you plug that in correctly, the signs come out. But bottom line for us, we find that when we put in electric field in the x direction, electrons don't want to flow in the x direction, which is usually what would happen if you put an electric field in that direction. Why? Because of the magnetic field. Instead, they all flow in the y direction. And so we find that there is a conductivity for applying an electric field in the x direction and a current in the y direction. But the conductivity for applying an electric field in the x direction and a current in the x direction is 0. Okay? So sigma xx is 0. Sigma yx is this quantity. Rho xx is therefore also 0. Rho yx is this quantity. And so we can now make a plot which is with the same axes as what we have in our data, right? So I can plot this resistance, R yx, which because I'm in 2 dimensions, let me move this up. Because I'm in 2 dimensions, the resistance Ryx is the same as the resistivity. Yeah.
Rho xx be infinity?
No, okay, so let me emphasize this. So usually when you say the resistance is inverse of the conductance, right, you're not thinking of it as a matrix with 2 by 2 components, right? So I usually say, oh, if the resistance is 0, the conductance is infinity, etc. But because so let's just do it. I have a 2 by 2 matrix for sigma, which is 0, 0. Let me call this quantity capital K. I think minus K, or no, plus K, minus K. Okay? So this is because I have 0, sigma xx is 0, sigma yy will also be 0, and this is xy and yx. So the resistivity tensor is defined as the inverse of this guy. So you see, when I take the inverse of a 2 by 2 matrix, I'll actually get 0, 0. Okay? So it's not particularly magic or meaningful. It's just that usually you're used to thinking about diagonal ones, and then indeed, if it has some conductivity, the resistivity will be the inverse of that. This is just because of the transverse thing. It tells you that. Yeah. So then you should always don't interpret rho xx being 0 or sigma xx being 0 without thinking about the whole matrix. Okay? So this is that. One more important fact about d is equal to 2 is that the resistance is the same as the resistivity. Because if everyone remembers, we usually learn that resistance is resistivity times L to the, I think, 2 minus d, because it's like rho L by A in 3 dimensions, etc. 2 dimensions is the special, it's special in that the resistivity and resistance are the same, independent of the geometry. And actually, this is an important part in the experiments, because experimentally they can only measure resistance. They can't measure resistivity. And because it's independent of geometry, it's the same as a measure of resistivity, and they don't, to get this high precision, right? This is really, really high precision. And it's basically limited by how well we can measure resistance, not by how well we can measure the geometry of the system, which is what would be in, say, in 3 dimensions, I would measure this quantity. Then I would have to measure L, whatever, sample boundaries to like 1 part in 10 to the 10, which no one knows how to do, to get a resistivity to that degree of accuracy. But 2D is special. You don't need to do all that work. And resistance is the same as resistivity. Okay? So I'll use the words interchangeably, and it's important to remember that they're the same in d is equal to 2. So coming back to the plot that we wanted to make, so we have that resistivity is the same as resistance is B over NEC. So when we plot the resistance versus magnetic field, we're going to find a straight line, which actually goes to 0. Right? And this is the classical Hall effect. If electrons are just classical and nothing else is happening, that data there shouldn't have any steps in it. Instead, it should be a straight line. Okay? Just one practical note, the classical Hall effect is used all the time to measure the density. You notice that the slope depends on n, if you know the charge of the carriers, or the charge of the carriers if you know the density. So it's usually a measurement that's done when you characterize a sample. Okay. So the classical Hall effect clearly doesn't do it. Classical doesn't cut it. So we need to take into account the fact that our system is quantum. So move everything up. How many of you have seen Landau levels before? So I know. Okay, like 4 or 5 of you. Okay. All right. So then I'm going to go through what a Landau level is now. So great. So now we're going to actually remember the fact that electrons are not classical; they're quantum. So that means they have a Hamiltonian, which looks like this. Plus 2m, where A okay, so everyone's seen, this depends on, sorry, x I have. So everyone's seen this Hamiltonian before, right? In the presence of an electric or a magnetic field, the way we generalize the p squared over 2m Hamiltonian is that we put in the gauge, the vector potential, A, and that's picking an A is picking a gauge. What's gauge invariant in our problem is this. Okay, so let's pick a gauge. We'll solve the problem in a particular gauge. It's called Landau gauge. I guess the theme of my lecture should be Landau, right? Like, that's like what connects the two topics. Anyway, so the Landau gauge is this. Pxy hat. It's easy enough to check that it obeys this. And just pictorially, so you can, let me plot it. It only has a y component, but the y component only varies in the x direction. So it looks something like this. Okay? So that's the particular gauge I've chosen. And also notice that I've treated, this is the independent electron approximation for the moment. Each of my electrons are just separate. They're not talking to one another. So we will put in interactions later. But for the moment, we're going to work in the non-interacting limit. So I may as well just solve the problem for each electron. And then do the usual thing of like once we get the single particle eigenstates, we then make Slater determinants of them to understand the many particle eigenstates. Okay, so I'm only going to, for the moment, I'll just solve the single particle problem. So one electron in a magnetic field. Okay, so using that vector potential, the Hamiltonian looks like this. Px squared. Actually, I'm sorry. Let's see what's there. Okay, right? This is clear to everyone. I just plugged in the fact that this is my vector potential. So this is the Hamiltonian that I now need to solve. So first nice thing about it, notice that it is translationally invariant in the y direction. Okay, so Hamiltonian commutes with Py. That's nice because then I know that my eigenstates are going to be labeled by a k, a momentum, and are going to have this form. It's going to look like a plane wave in the y direction, and then there's going to be some function that depends on x. Okay, so that's nice. We plug it into this, and we find that the Hamiltonian becomes, we need to solve hk, fk is ek fk.
Sorry, what's HK again?
I'll write it down. Small hk, right? I haven't written it down yet. Which one's this? Where? Where hk it's basically the same Hamiltonian except for Py I substitute h bar k. Okay? Okay, great. So now we have to solve a one-dimensional problem in Px and x. So in fact, this is a familiar problem. We know exactly what it is because it's the harmonic oscillator, right? I have a quadratic term in momentum, a quadratic term in position. This is the operator x hat. And this is the canonical problem that we all know how to solve. So that means I know what fk is. And so actually, let me write this down in a form that looks more like the harmonic oscillator. X plus KLB squared. So I just defined a new quantity called the magnetic length, LB. It's this particular combination of EB, H bar, and C. Yeah. Oh, okay. Yeah. Okay. So this is the more familiar Hamiltonian of a harmonic oscillator. Notice our cyclotron frequency that we found in the classical electron problem has turned up as the frequency of the harmonic oscillator, omega c. There is a new length scale in the problem. It's called the magnetic length, and it's defined as so. And basically what this length scale does is it shifts the center of the harmonic oscillator to this point. And so I define xk to be the center of this harmonic oscillator, which is equal to minus k LB squared. Okay? So just to iterate, I have a harmonic oscillator with three parameters: frequency omega c, center of the oscillator xk equals minus k LB squared, and LB a new length scale known as the magnetic length. Yeah.
One thing, you're specifying here boundary conditions at infinity, right?
So right. I'll come back to it. Yeah. So the one boundary condition that I have specified by picking this is that it's periodic in the y direction. Right, so that much is, I don't know where it went, but it's periodic in the y direction. In the x direction, I'll come back. Okay. So now I'm going to. So the energy of each k mode, so right where k was parameterizing the momentum in the y direction, is given by the energy of a harmonic oscillator, which is n plus half h bar omega c. N goes from 0, belongs to an integer, right? And the eigenstates are e to the I k y These HNs are the Hermite polynomials. Okay, sorry, step back. What have we done? We've solved the single electron problem in the presence of a perpendicular magnetic field. We found in a particular gauge, it looks just like the harmonic oscillators. So here are the energies. These are the eigenstates. Okay, so now let's try to understand what this looks like. Okay, first important observation, the energy is independent of k, right? So it depends only on n, which is the level in the harmonic oscillator. So if I plotted the spectrum versus k, or equivalently xk, right, where xk, remember, is the center of this this eigenfunction. And you see that I just have flat levels. Right? This is the n is equal 0 level, 1, 2. This gap is h bar omega c, and the energy is completely independent of the momentum in the y direction. Okay? So these are our Landau levels. Each, all the energy eigenstates at a given value of n forms a Landau level. Okay? And so the first thing we see is that each Landau level is highly degenerate because of this large number of k's allowed for each n. So let's count this degeneracy. So this was my xy plane with my magnetic field in the z direction. And I have periodic boundary conditions in the y direction. And so now to the question of what were the boundary conditions in the x direction. So formally, we've actually kind of solved it, assuming it's these boundaries are infinitely far away. Okay. Now we're gonna make an approximation. We're gonna say, actually, we'd like to know what the states look like for some with Lx. Okay. And what we're gonna do is we're gonna take all these wave functions, and whichever ones fit within this distance Lx, we're gonna say are okay. The other ones that don't fit in it, we're gonna say are not okay. Yeah.
But then I have a problem here, because if I choose this gauge, right, it's somehow this gauge it's breaking the translational symmetry in the x direction.
Yes.
And it's giving me only symmetry in the y direction.
Yeah.
But I can choose another gauge in which I can restore another symmetry, which is the rotational symmetry.
Yeah, we will do that on Friday, yeah.
Okay, but then here you're choosing to solve the system in a torus, right?
No, I'm solving it on a cylinder.
On a cylinder, okay. Okay.
Yeah. So the cylinder does differentiate between x and y,
Right.
not the torus. And indeed, you can, through gauge transformations, you can make it look rotationally invariant, and make it look. In the end, the reason I recover translation invariance is because all these levels are highly degenerate. So any superposition of them is also a good eigenstate. And in particular, I can make a superposition that's translation invariant.
All right. So what you're saying is that I can relate by a gauge transformation states in the cylinder and states in the infinite plane, right? But if I consider periodic boundary conditions in both directions, I have the thing in the torus, and the degeneracy of Landau levels in the torus is finite. It's not infinite, right?
No, so it's not going to be infinite for me either, because I'm going to put it on a. So I'm doing something slightly approximate, which is that I solve it in the infinite plane. Then I say, oh, the degeneracy on a finite cylinder. Oh, sorry, I solve it in the infinite cylinder. Then I say the degeneracy of a finite cylinder is approximately determined by all those eigenfunctions here that lie within my cylinder. Okay? So maybe a picture of these eigenfunctions will help. What this thing looks like is in the xy plane. So let me just pick the n is equal to 0 Landau level. So then I can forget about this Hermite polynomial. So there's a Gaussian in the x direction about the center xk. Right? And in the y direction, if I plot mod psi kn k0 squared, it's just uniform. So this is a picture of the wave function. It's highly localized in the x direction, completely delocalized in the y direction. And the width here is set by the magnetic length. Sorry, I don't know if you can see that. The width is the magnetic length. So it's not such a bad approximation if I work in a strong magnetic field where this is very small to say that, OK, these wave packets are really localized, so I'm going to allow all those states that fit in here. Sure, I may make an error at the boundary, but it's going to be a really small error because these packets are really tightly localized. OK, so it's and
it's okay if you want to describe the bulk of the sample, right?
Yeah.
Which is what you want.
Yeah.
But changing the topology of your space have serious consequences on properties of the states. Right?
No, it has. So the topology of the overall manifold we'll see on. Well, actually, for the integer effect, it doesn't matter really. For the fractional one, also, I mean, it's going to affect global properties like degeneracies, etc. It does not affect local properties like, for example, this conductivity that I'm going to calculate. That doesn't particularly care about your boundary conditions. We'll see that in the periodic sample as well as the sample with edges. So it depends on what you want to do. If you want to get global properties right, indeed, I should do it right. But locally, it doesn't matter. OK? OK, but this picture of the wave function as gauge is important. OK, does everyone see this? Highly localized in the x direction, delocalized in the y direction. So that if I, on this picture, for each k, I can plot where the center of the wave function is in the x direction. And it's like here, 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 depending on the value of k. OK? So the way we're going to count the degeneracy is we're going to ask how many of these wave functions, what are the values of k, such that the center xk lies between minus Lx over 2 and Lx over 2, where Lx is the length in the x direction. If the center of the wave function lies within minus Lx over 2 to Lx over 2, then I know that this eigenfunction that I found lies on the cylinder. Okay? And so this is going to give me an estimate of degeneracy. Let's count it. So number of states in a Landau level, LL Landau level. Actually, I should say in each Landau level. Is the sum, I sum up all those k values that such that xk lies between minus Lx over 2 and Lx over 2. Okay, so that means k is okay. where I just use the formula that xk is minus k lb squared. And times 1. So I just add 1 up for every state that's allowed, and it's in my cylinder, making this an integral dx. This is the discretization in k, and it has the same limits. Lx over 2 lb squared. And when I do this integral, I get that the number of states in each Landau level is Lx Ly over 2 pi lb squared. Okay? I can rewrite this as actually b times Lx Ly over phi 0, where phi 0 is defined to be the flux quantum, hc over E, and has a physical meaning as the flux enclosed within a, if you drew a circle of, roughly speaking, of having the area of 2 pi lb squared, okay, which is lb, remember, is a magnetic length. So this length gives you an associated area. And if you ask how much flux penetrates this area, it gives you a fundamental unit of flux called the flux quantum. And so this is another way to write down what the degeneracy is. OK, so what we've found is that these highly degenerate Landau levels, there are highly degenerate Landau levels whose degeneracy, number of states in each Landau level, is extensive in the area of the system. Okay, Lx Ly is the area of the system. And so we have an extensive degeneracy in each Landau level. Another way to say this is that in every Landau level, there is one state for every flux quantum, phi 0. Because this is the total flux piercing the system. Phi 0 is the unit of the flux quantum. So if you divide the total flux by phi 0, you get the total number of allowed state. Okay? Is this okay so far? Yeah.
Can you say again why we divided by 2 pi Ly when we went from the sum to the integral?
Basically that because in this sum, the k jumps by 2 pi over Ly. Because I have, right, when I put a k on a, because the length in the y direction is Ly, so I know that k has to be quantized. K is 2 pi over Ly times an integer m. And so what I'm saying is that the maximum value is this. Then in units of 2 pi over Ly, I can go up all the way to this. Does that make sense? It's the same reason that usually that whenever you have a sum over k, 1 over length, you can make it an integral. It's the same reason that I've done it. Yeah.
So at the end, we're dealing with electrons, so there are spin degrees of freedom.
So at the moment, we assume that they're spinless. Okay, so only because experimentally it's important. Okay, sorry, let me say this way. We can do the same analysis for spin up and spin down. What we'll find is Landau levels for each, which are split by the Zeeman energy. Okay? The phenomenology of exactly what happens with spin and without is different. So for our purposes, let's assume that the spin degree is frozen out.
Okay, so up to here, you have to make no assumption about B being small.
No, I haven't. And so I'm now going to connect to the classical case where B is small, we'll find it looks classical. Yeah, but this is the solution of the problem, no matter what B is. Okay. Okay. So I need to go here. Okay, so let me refine the picture of the wave functions that I drew to be more correct in the high field limit. Okay, so remember I said that in the xy plane, this is the wave function at with momentum k in the y direction, and it's going to be localized about xk. So this is xk prime, and it has width given by the magnetic length. However, the spacing between adjacent orbitals, and I mean by adjacent, I mean take k prime is k plus 2 pi over Ly, right? So just one value of k and then the next allowed value of k. Clearly, because xk is minus k Lb squared, this just means that I'm going to move the, actually this means this is xk and this is xk prime. I just move the center over by some small amount, right? And the small amount is actually, so delta x, which is the spacing between the centers of two adjacent eigenfunctions, is given by 2 pi over Ly times Lb squared. Okay, and this you can see is clearly much, much smaller than the width of each of the wave functions, which is the magnetic length. Is this clear? And that the reason that's true is because the magnetic length is much, much smaller than the size of the system in the y direction if I pick a strong field. Okay? So that means the more correct picture, instead of drawing eigenfunctions centered around different points which are well separated, the more correct picture is that I have overlapping lambda orbitals. This is in the they're again delocalized in the y direction, right? So there's the amplitude square doesn't depend on the y direction at all, but in the x direction it has a Gaussian profile, but these Gaussian profiles overlap strongly with one another because the spacing between the adjacent orbitals is much, much lesser than the width of the orbitals. So this is the right picture you should have in mind. Nevertheless, these eigenfunctions are all orthogonal to one another. They were, after all, the solution of h psi z psi because of the fact that they have different momenta in the y direction. So this one has momentum e to the I ky, this one e to the I, different one, k prime y, et cetera, et cetera. And that's why they're all orthogonal to one another, not because they don't overlap in the x direction. Okay? So it's just useful to have this picture in mind that there's many of them all on top of one another when the magnetic length is smaller than Ly. Okay. Then just a few numbers in the gallium arsenide samples. So the magnetic length has this form. Angstrom. Okay, that maybe is a weird way to write it. But at 10 Tesla, which is a pretty strong field, and you should look to see in the y-axis of the plots to see that it goes from many Tesla going up to 12, 15 Tesla. So these are really strong fields. At 10 Tesla, if you plug that in, you find that the magnetic length is around 80 angstroms. Okay, so pretty small to be compared to the interparticle inter-electron spacing, which we said was around, which is in the nanometer scale. So you see that this length is truly microscopic at the strong magnetic fields that we're going to work at. Again, the mean free path, L, was in millimeters. So that's still the longest length scale in the problem. Okay. in terms of energy scales, the cyclotron frequency omega c at 10 Tesla is about 200 Kelvin. The experimental temperature is 80 millikelvin. So for the purposes of the experiments, usually one does not worry about higher Landau levels. If the, where's my picture? If the density of the electrons is commensurate with being just occupying the lower Landau level, one can actually forget about higher Landau levels. And that's because to excite different Landau levels, you'd have to be at these temperatures, whereas you're working at some really, really low temperature. Okay, so, and theoretically, this is an approximation that's also commonly made, which is the lowest Landau level approximation. It's called LLL, I guess, lowest Landau level. And it comes from the fact that this energy scale is huge. Most of the time, the physics and the temperatures that you're at, it's sufficient to consider just a single Landau level. Yeah. Go ahead.
So I guess sort of two related questions. One is like in most experimental parameters, like the density of electrons, it's not going to be like just the lowest Landau level.
No, it need not. So then it's whichever is the conduction Landau level.
So, like
so
the
say,
highest level.
Yeah. So the highest occupied Landau level.
And then so then the related question is how do you know it's going to be partially filled? It's like it could be partially filled, right? You don't know it's going to be completely filled.
So this parameter nu that we introduced before, that's the filling fraction. So remember that the degeneracy of a Landau level is this guy here, right? So I have these many number of states in each Landau level. So I can define an important number, nu, which is the number of electrons divided by the number of states available in each Landau level. And so the value nu that you'll see is actually related very closely to how is it, if this is 1, that's a fully filled Landau level. It's 1/3, it's partially filled. But we keep track of this number. Okay, yeah.
Can you repeat what you said, that the right picture to have is that you have the overlapping wave function?
Okay. So the idea is that the width of each wave function is set by the Gaussian. Okay. So actually I can tell you that for in any Landau level, it actually is square root n LB. Okay. And so this is the width. And we have another scale in the problem, which is the spacing between the centers. Right? So if the spacing between the centers is much lesser than the width, that means all these orbitals are they're highly overlapping with one another. Right? So this picture to be contrasted with something like this. If the spacing was much bigger than the width of each wave function, they look separate. Whereas because the magnetic length is much, much less than the length of the sample, the picture is actually this. Spacing between them is much lesser than the width of each one.
For a fixed magnetic field.
For a fixed magnetic.
If I have strong magnetic field, then I recover the same non-overlapping.
No, it's the opposite limit. So a strong magnetic field, it's useful to remember LB is proportional to 1 over square root of B.
Yeah.
Strong magnetic field, smaller magnetic length, better this. This is the picture. Weaker magnetic field, this is the picture. So where we're thinking about experiments in a phenomena, this is the picture. Spacing much lesser than width. And I mean, and I want to emphasize, the width itself is small, it's going down, but I'm asking about a ratio of two quantities. What is the ratio of the spacing between them as in the units of the width? So I'm not so interested that the width, absolute value of the width itself is going down.
The spacing is fixed, right?
No, the spacing is, itself depends on the magnetic length because of,
Oh, okay.
yeah. So they both are going down. It's just the spacing goes down faster. Okay, I will leave it at that. Can you get more?